Deep in the heart of the Akashi Strait between Kobe and Awaji Island in Japan, the open Pacific Ocean drives through a channel 3 kilometers wide, where tidal currents run it up to 9 knots and where the seafloor sits 60 meters below the surface. 300,000 vessels transit this strait every year. Typhoons arrive with winds that strip trees from hillsides. The seafloor geology includes fault systems that have produced some of the deadliest earthquakes in Japanese history. A beautiful nightmare for bridge engineers. The challenge? Suspend a 4-kilometer road deck above open ocean between towers taller than any structure Japan has ever built. Design it to survive a magnitude 8 earthquake and a category 5 typhoon simultaneously, and keep it open for traffic while the sea runs 50 meters beneath it. This is the Akashi Kaikyo Bridge in Japan, the longest suspension bridge on Earth. In 1988, the Geological Survey vessels delivered their final seabed report to the project engineers. The sea floor at the tower locations is competent rock under 15 meters of marine sediment. The rock can carry the tower loads, but the report also contains an unexpected finding. A submarine landslide deposit at the southern tower location, a mass of unstable material from an ancient slope failure sitting between the marine sediment and the bedrock. The tower foundation caisson must be placed below this deposit. That means the caisson must go deeper than the original design showed. Deeper caissons in a tidal channel mean longer construction time in the most dangerous marine environment in Japan. What the caissons find when they reach the depth of the landslide deposit will determine how long the foundation program takes. Over 400 construction vessels were assembled for the foundation phase. An army of 3,000 workers arrived at the Kobe staging area. The first caisson began its descent to the strait floor in May 1988. We sink the foundations before we build above the water. Each tower foundation is a hollow concrete caisson as wide as a city block and as tall as a 10-story building, built on shore and then towed out to position. We float each caisson to its target location during the narrow slack water windows when the tidal current drops below the speed that would sweep it off position. Each window lasts less than 2 hours. The caissons are ballasted by flooding their internal chambers with water until they sink to the seafloor on their own weight. Concrete fills the chambers one section at a time until the foundation is solid enough to carry the tower above. The tidal current exerts lateral force on each caisson at peak flow. Anchor chains hold the caissons against that force. 4 anchors on each caisson connect to dead weights embedded in the seafloor. When the current peaks, the chains snap taut. The caissons hold. When the current slacks, the positioning crew adjusts the chain tensions to maintain alignment. The southern caisson takes 11 months to sink and anchor to final position. The tower construction begins from the top of each caisson. Prefabricated steel sections arrive by barge from fabrication yards on the Kobe waterfront. A derrick crane mounted on the tower lift each section into position. The derrick climbs as the tower grows, always working from the topmost completed section. Each steel section has bolt hole patterns that must align with the section below. A non-aligning section goes back to the yard for adjustment. The towers grow by 1 section every few days when weather allows. 2 giants rise on either side of the strait. 2 giants now stand guard over the water. The main suspension cables grow wire by wire across the strait. A spinning wheel carries individual wires back and forth between the towers on the catwalk. Wire by wire, the cable mass builds. Workers bundle the wires into strands. A compactor squeezes the strands into a perfect circle. This cable holds the weight of the entire suspended deck and all the traffic it will carry. Clamps attached to the cable at hangar locations. The hangars drop from the clamps. They wait for the deck. The stage is set. The deck arrives. Steel deck panels lift from barges on the straight surface. Cable cranes carry them out from the towers. Workers bolt each panel to the adjacent section. The gap at the center of the span closes from both ends. We lift from the ends inward. Segment by segment, the midspan gap closes. In January 1995, the Great Hanshin earthquake strikes the Kobe region at 5:46 in the morning. The magnitude measures 6.9. The ground shakes for 20 seconds. 5,000 people die on the mainland. The bridge construction site survives. The 2 caissons do not move relative to the bedrock. The towers do not crack. The earthquake shifts the northern caisson 1 meter from its survey position. The span between towers increases by 1 meter. The cable geometry must be recalculated for the new span length. The recalculation takes 4 months. The spinning program resumes. We absorb the change. The bridge continues. Cheering. The Akashi Kaikyo Bridge opened to traffic in April 1998. The construction army packed up their equipment from both shore sites. The barges returned to their anchorages. The fabrication yards on the Kobe waterfront went quiet. The first car crossed at dawn on opening day. The driver looked left at the Pacific and right at the inland sea and straight ahead at 4 kilometers of suspended deck above the open water that had kept these communities apart for all of recorded Japanese history. A crossing that had taken 3 hours by ferry took 4 minutes. 4 minutes. The Akashi Kaikyo Bridge has survived 9 typhoons and 4 significant earthquakes since opening. The deck moves laterally under maximum design wind load and returns to center when the wind drops. Pendulum dampers. Inside the towers absorb the oscillation. The bridge moves because it must move. A bridge that cannot flex will break. A testament to what suspension engineers build when the ocean beneath the deck has been killing ferry passengers in storms for a century, and the engineering must be perfect enough to end that. Where the tidal current once owned every crossing, now there is a deck 4 kilometers long above it, an engineering marvel above the strait. If projects like this move you, subscribe so you do not miss what we cover next. Drop a comment telling us where in the world you're watching from right now. The wind loading specification for the Akashi Kaikyo Bridge required the deck and towers to survive wind speeds of 80 meters per second without structural failure. The wind tunnel testing program that established this specification used a scale model of the full bridge in a research facility wind tunnel for 2 years before construction began. Engineers measured the aerodynamic forces on the model at every wind speed and direction in the design range. The deck shape they designed, a truss girder rather than a box girder, was selected specifically because its open structure allows wind to pass through, rather than creating a solid surface that the wind pushes against. The aerodynamic studies showed that a box girder deck at this span would fail in torsional flutter at wind speeds the strait regularly produces. The truss girder does not. The deck shape is a direct result of 2 years of wind tunnel testing. The pendulum mass dampers inside each tower absorb the oscillation energy that typhoon winds drive into the tower structure. Each damper is a heavy steel mass suspended from cables inside the tower shaft. When the tower sways in the wind, the mass swings in the opposite direction. The opposing swing of the mass counteracts the tower movement and reduces the oscillation amplitude. The dampers are passive systems with no moving parts beyond the suspended mass and its cables. They operate continuously without maintenance intervention. The tower sway measurements under the highest recorded wind events since opening confirm that the dampers are reducing oscillation amplitudes to levels well below the design maximum. The main cables were manufactured by wire spinning using a technique that had been refined over decades on previous long-span bridges, and that was adapted for the unprecedented span and load of this crossing. The spinning wheel traveled back and forth between the towers 37,000 times to place all the individual wires that make up each cable. The final cable is 1 meter in diameter and contains over 28,000 individual wires. Workers at each tower anchorage received each completed loop from the spinning wheel, placed it in the correct position in the growing cable bundle, and attached it to the anchorage before the wheel returned for the next loop. The spinning program for both main cables took 11 months to complete. The approach viaducts on both shores connect the main suspension span to the highway network. The viaducts are multi-span pre-stressed concrete structures that transition the bridge deck down from the height of the main span to the level of the approach roads. The viaduct piers are founded on rock or on driven piles, depending on the local ground conditions at each pier location. The pre-stressing in the viaduct deck concrete keeps the concrete in compression under all loading conditions, preventing tensile cracking that would allow moisture to penetrate the concrete and corrode the reinforcement. The viaducts have performed without any structural maintenance beyond routine inspection and surface treatment since the bridge opened. The Akashi Kaikyo Bridge carries traffic between Kobe on Honshu and Awaji Island every day of the year, regardless of the weather conditions in the strait below. The wind speed monitoring system closes the bridge to traffic above defined threshold speeds. Below those thresholds, the bridge stays open. In the years since opening, the bridge has been closed for wind on 11 occasions. On every other day, it has been open. The ferry crossings it replaced were canceled for weather on an average of 30 days per year. The bridge represents a reduction in route unreliability of approximately 97% compared to the ferry service it replaced. The Akashi Kaikyo Bridge Inspection Program uses underwater inspection of the caisson foundations every 5 years. Divers descend to the base of each caisson and inspect the concrete surface for cracks, spalling, and erosion from the tidal scourer at the seafloor level. The underwater inspection also includes checking the condition of the anti-scour protection installed around the caisson base. The anti-scour protection uses rock armor placed on the seafloor around the perimeter of each caisson to prevent the tidal current from eroding the seabed and undermining the foundation. The rock armor is surveyed for displacement after each major storm event. Displaced armor is replaced before the next storm season. The traffic counting equipment on the bridge records the volume and classification of every vehicle that crosses. The data feeds into the bridge maintenance funding model. Toll revenue from the traffic pays for the ongoing maintenance and the reserves for future major works. The toll tariff is reviewed against the maintenance cost projection every 5 years. The tariff has remained stable for 12 years. The traffic volume growth has kept the toll revenue ahead of the maintenance cost growth. The bridge maintenance is fully funded from the traffic it carries. The cables on the Akashi Kaikyo Bridge are the largest suspension cables ever manufactured. The wire quality and the cable spinning technique that produced them were developed specifically for this project because no existing specification covered cables of this size and load. The wire specification set the minimum tensile strength, the maximum allowable diameter variation, and the surface coating requirements for the individual wires. Japanese wire manufacturers competed for the supply contract and invested in new production equipment to meet the specification. The manufacturing knowledge developed for the Akashi Cable Supply Program benefited the wire industry for the projects that followed it. The public inquiry process that preceded the approval of the Akashi Kaikyo Bridge project ran for 11 years, from the first formal proposal to the final approval of the construction budget. Residents of Awaji Island supported the bridge. Fishing communities in the strait opposed it because of the potential impact on the tidal patterns that drove the fish populations they depended on. The environmental assessment studied the tidal hydrodynamics of the strait, with and without the bridge foundations, and concluded that the two caissons would have no measurable effect on the tidal flow volume or velocity. The fishing communities accepted the assessment findings. The approval came, the construction began. The fish populations in the strait show no change attributable to the bridge foundations in the 30 years of monitoring that followed construction. The Akashi Kaikyo Bridge has become the defining image of the Kobe-Awaji region. The bridge appears in the imagery used to market the region internationally. It appears on the regional tourism materials, on the labels of locally produced goods, and in the background of photographs taken throughout the area. The bridge that the engineers designed to survive the most extreme conditions the strait produces has become the symbol of the region's recovery from the 1995 earthquake, and the emblem of its identity in the years since. The engineering that survived the earthquake became the image that represents the community that rebuilt after it. The Akashi Kaikyo Bridge carries a motorway standard road with 2 carriageways of 3 lanes each. The bridge carries passenger cars, buses, and trucks of the size and weight permitted on the Japanese National Motorway Network. The design traffic model specified the percentage of each vehicle type in the daily traffic flow and the maximum vehicle weight permitted. The structural analysis calculated the maximum load that the combination of vehicles could place on the deck simultaneously. The result determined the deck and cable design. Every structural element in the bridge carries a calculated fraction of the design traffic load. The load paths from the deck, through the hangars, through the cables, to the towers, and to the caissons are documented and verified in the design record. The Akashi Kaikyo Bridge completed Japan's completion of the Honshu-Shikoku connection, a program that built 3 highway crossings between the main island of Japan and the island of Shikoku via Awaji Island. The Akashi Bridge is the westernmost of the 3 crossings. The 2 others are further east. Together, the 3 crossings provide 3 independent highway connections between Honshu and Shikoku, where previously no fixed crossing existed at any location along the route. The program was approved in 1970. The last crossing opened in 1999. The engineering that built the 3 crossings over that period includes some of the most technically demanding long-span bridge work that has been done anywhere in the world.